Hi, my name is Julia Silge, and I'm a data scientist and software engineer at RStudio. And in this screencast, we're going to use this week's Tidy Tuesday dataset on post offices in the United States. And we're going to train a text model, a supervised machine learning model with where the features are text data, features that we have created from text data. We're going to use Subword information that we're going to create via tokenization to subword unit, so in between character level and word level. And then we're going to train a model, a classification model, to classify the post offices, to learn whether they are in Hawaii or they are in the rest of the United States. So Hawaii, obviously, like a really unique place when it comes to culture and language. So hopefully that sets us up for success when it comes to training this model. And along the way, we can learn about this kind of tokenization, about how to train this kind of text model.
Okay, let's learn something about post offices in the United States. So I am going to load this week's Tidy Tuesday data about post offices. This is a pretty interesting data set, I think. It has got all this really interesting information, like the name of the post office, where it is, what state and county, when it was established, when it was stopped, when they stopped using it. And then there's information here about more geographical information about when it where it is, if they were able to link it up and whatnot. So what I want to do is train a text model. So a predictive, use tidy models to train a model on the text using this really short text that we have here in the name. And I want to connect it to the state. And I want to see can I see if it is possible to connect the state that we have here to the name. So let's look at what we have, what information we have here in the state. So first, let's look at the names. So there are, of course, a lot of very unique names. There are duplicates. These are, names of post offices across the United States. And then let's see where has the most post offices in this data set. Okay, so Pennsylvania, then Texas, Kentucky. This is actually kind of interesting to think about, like what contributes to a place having more post offices versus less. I don't know. Some of these are populous states. And then, of course, how long have they been populated and whatnot? So pretty interesting question here. Okay, so what I want to do is to build a model connecting the names to the states. And so what I want to do here is say, can I identify one state's post offices relative to the rest of the state's post offices? And I want to set myself up for success here by trying to do the easiest ones. Although in some ways, this might not be easy because there's not actually that many. So let's just stop and think a little bit. What states post office names do you think are the most distinctive? Like if I train a machine learning model, what states post office names do you think my machine learning model will have the best chance of being able to find? I think the answer is Hawaii, because Hawaii has Hawaii is a culturally unique place, is unique in terms of culture and language. So if we look at these names here, these names look very distinctive, right? Like if I said, I'm going to the I'm going to the post office named, Kilauea, you might say, oh, I'm guessing that's in Hawaii, right? So these are very distinctive. Many of them are. What I want to do is I want to try to train a model that looks at these kinds of words and is able to try to learn that they are Hawaiian post offices in Hawaii compared to, these up here. Midway, Hamilton, Franklin, and whatnot. And you do that using a certain kind of tokenization. So let's get started here. So I'm going to load tidy models, and I am going to do a split here. So let's split into training and testing. So I am going to take the post office data set. I'm going to take the state variable. And I'm going to change it. So when state is Hawaii, it's called Hawaii. And then all the rest of the time, it's called other. So I'm making a new two-class variable, and I'm just going to select name and state, and these are my two variables, and then I'm going to do an initial split, and I'm going to stratify on state because, as I'm sure you are guessing, this is a very imbalanced data set, like super imbalanced, right? There are, if we go back up to this here, Hawaii is probably one of the very smallest. So in some ways, this maybe is the easiest choice, right? Because Hawaii is very distinctive. But in some ways, this is difficult because I have very few examples here. So we'll need to account for that in how we train a model and also how we evaluate our model. Okay, so let's make our training data set, training on the split. Let's make our testing on the split. And then let's make resampling. Let's make some folds, some data folds of resampled data sets to use for our model training purposes. So let's call this post office folds. Okay, so this part here is what I kind of think of as like spending our data budget. We split our data, we make training and testing, and then we make data resampling, resamples from the training set. Okay, next let's go on to feature engineering and data preprocessing. So we're going to use two add-on packages for tidy models, text recipes, and themis. So text recipes is for dealing with text, and themis is for dealing with imbalanced data, which we for sure have here. So we are going to start by starting a recipe. So we're going to predict state from name. And the data that we are going to use here to learn about data types and whatnot is the post office training data. And so we're going to tokenize here. Tokenize here. And so what we're going to tokenize is that name data, which remember is very short. But we're not going to tokenize using the default tokenizer. We're going to tokenize using tokenizers.bpe. And what BPE stands for is byte pair encoding. And so this is an algorithm that instead of just breaking apart, say, the names, instead of just taking these names of post offices and breaking it apart into characters or, words, right? Schofield barracks or whatever. What it does is that it identifies subwords. So it iteratively merges together frequently occurring subword pairs to find subwords that are important in your data set. So it gets you kind of at that space in between character level and word level information. So this kind of subword information is important in a lot of the really big language models that are used on like in the state of the art these days. And another benefit of it is that it can actually handle new or unknown words at prediction time, which like bag of word models often, or like word models that deal with tokenization often can't. So there is a hyperparameter for this, and in the interest of time, I'm not going to tune this hyperparameter. I am just going to set it, and that is how big of a vocabulary are you going to use? So I'm just going to do a small one because this is such a small, like we are not, we like this is just names of post offices, so we don't need a big vocabulary. So I'm going to go very small on the vocabulary size here because this is such a limited data set. But this right here is a hyperparameter of the model. And so this is something that you can tune in tidy models, but we're not going to tune it. I'm just going to set it here. Okay, so now I'm going to filter and only keep those 200. I'm going to weight by the frequency on how often are those subwords used in each of these post office names. And then I am going to normalize all the predictors here. So all of these, which is going to be all these subwords. And then I am going to downsample. So what does that mean? I'm just going to throw away data, which is a lot of data, but because we're going to be doing this with resample data to evaluate, it's going to keep different sets of the majority class each time. So we could use various kinds of upsampling if we prefer, but I'm just going to downsample, literally throw away tons of data of those other post offices here. So let's set up this recipe, and I am going to, I think this will run in a reasonable amount of time. I'm just going to show you what the output of this looks like, so you can see what it does. So what it's tokenizing, it's finding the subwords. It is now it has a now we have a tibble of the results here, and the column names are all the subwords. So look, Grove, and so some, so this is now super tiny data, right? So Grove, Mill, AKW, and these characters mean that I think it's at the beginning of the string. So BERC, AKE, springs. So these are the subwords. And so some of them are long, they're of different length. So the algorithm learns what the subwords are. And notice it goes on because we have more. So we've got 200. So this isn't great. I wonder if instead of step downsample, maybe we'll do something else. I don't love that. We're going to do step. Let's try like step rows or step smote. Yeah, let's try one of those instead. So this one I think will be good. Let's do this one instead. Whoops. Because we're just throwing away so much. Step smote. And let's see what that does, if that works. And this, instead of throwing it all away and ending up with such tiny data, yeah, this is better. Let's do this. And do we still have the state somewhere? We should. Okay, I think that's a better way to go because now we have, that looks much better, you know, for what we're going to try to fit here. Okay. All right, so that's our pre-processing, our feature engineering. Now let's make a model. So we're going to do a linear support vector machine. So this has some pretty nice characteristics. We're going to use classification because our model is training. Is it Hawaii or not? And the engine here is lib linear. So this is a newish Parsnip model. It is in the current development version of Parsnip, so you'll need to get it from GitHub. It will be going to CRAN fairly soon. So linear SVMs work pretty well for text in a lot of situations. And this engine is quite fast, so this should work pretty darn well for us. I expect to get good results. This is a good option, a good sort of, linear option for text in a lot of situations. And now let's put these together in a workflow. So I'm going to add my recipe here. I'm going to add my model, SVM spec. And so this is now my workflow, post office workflow, like so. So it's got a recipe, it's got a model, and now I can, so one of the great things about a linear SVM is that the tuning parameters don't really have much effect, like it doesn't do much. So I am going to just fit to the resamples. So I do the workflow, I do the folds, so I don't need to really tune anything. One sort of less good or nice thing about this liblinear is that it does not have it does not return class probabilities, just hard classes in the results. So we need to use metrics that, for example, we can't do ROC curves. So we just need accuracy, and then let's do like sensitivity and specificity here. And so let's call this post office results, like so. So let's start this and let's talk about what it's doing. So it is for this workflow, it is for every fold, every one of our 10 cross-validation folds, it is going through and it is finding subwords, normalizing. We needed to normalize because we're doing this support vector machine. Is very important for support vector machines. Upsampling and then fitting to this support vector machine. And then it's going to compute these results here. And so after we do this, we'll be able to say collect metrics for our post office results here. So this is going to take just a little bit of time to fit because it's pretty big data now, and it's having to go through and do it 10 times. So I'm going to pause the video and then I'll come back when it's done. Okay, we are back. So this fit all of these models to, or all of the support vector machine models to all of these resamples, and here are all our results. So you can see that with the way that we set up this this feature engineering, it is having a harder time with one of the classes than the other. And of course, with the way the imbalances, it makes the accuracy really good. So let's fit one more time. And so let's use last fit. We don't have to, so there's nothing tunable in here. So we'll just say last fit. And then we send in the split. And so it will train one more time on the training data. And then let's call this final fitted. See, I don't really like the way that looks. Let's do that. something. I don't know, something like that. So let's train this. So it's gonna fit this one more time on the training data, and then evaluate on the testing data as we have here, and then we'll be able to look at this, see if we get about the same metrics, and then explore our results on that on that testing data that we have. So we'll say collect metrics of final fitted, and then we can start to do things like we cannot make an ROC curve here because we don't have class probabilities, we only have hard class predictions, but we can do a so if we do collect predictions, we can do collect metrics, we can do collect predictions, and then after we have the predictions, we can do something like a confusion matrix. So the confusion, our predicted, our real value is state, and then what we'll have in here is we'll have something called predicted class here, and then that'll give us a little, just like a little printout, and then we can make a plot. It has an auto plot method. And for something that's so imbalanced like this, we'll need to do a heat map like so. And well, let's see, it's fairly, we're fitting on some biggest data, so let's see how long it takes to fit here. So when we can look at the metrics, I don't wonder if I should pause the, okay, there it goes. Okay, so let's look at the metrics. Oh, it helps if I spell it right. Okay, so we get about the same results as we got on the results overall. And then if we can look at the confusion matrix like this. Again, it would help if I spell correctly, like so. Okay, and so we see that it has learned, so the model has learned, it's doing pretty well here on other, and it's doing, it's not so bad on Hawaii. Remember, if we remember what the Hawaii names looked like, it probably is hard to know whether Roosevelt goes in Hawaii or not, right? Whereas some of these other names that are more from the native culture of Hawaii are going to be easier for the machine learning model to look at there. Okay, so we can make a visualization of this, right, where we see, okay, we can see how, so here's the true values here. So we want more things in this box than this box, and more things in this box and this box. We can understand how the model is doing. And now let's, since this is a linear model, we can actually get out what is in those results there. So let's do pull workflow fit. So we've got final fitted. There's this workflow object here. And unfortunately, we have to do that, which I know is not very pretty. But so let's call this the fit. So this is a parsnip fit object like that. And then we're gonna make this a little better. So this is a little bit temporary. So inside this parsnip fit object is the liblinear fit object, and it has this which is all the coefficients. So let's call this the liblinear object. So basically there's no tidier for this right now. And we're going to make one and add it somewhere. I don't know. But so let's do that. And then let's make a data frame. So right now that's a matrix. So let's make a data frame. And so let's say Tibble. And so we want something called term. And term is going to be the call names of that thing. And then estimate is going to be just that thing. Liblinear obj. Right? Did I do that right? Oh, almost. Okay. Like that, I think. Yes. Okay, great. So here are all these terms. these subwords, and here's the estimate. So now we can do things like arrange estimate. So here are the things that are associated with being more, let's see, which way does it go? Whoops. So here are the things that are more Hawaii. Here are the things that are less Hawaii. And we can make a little, to finish up, let's make a little visualization. We want to take out the bias here means the same thing as intercept. And so let's group by the sign, whether it's positive or negative. And let's take for the positive and negative, let's take like the top 15 like this. And then we can ungroup, and we can change. We don't need all that stuff. So let's do string remove, and in string remove we'll say term from return. We're going to remove tf underscore name underscore, like that. So now we have just the subverbs, and we can do just like a quick visualization where we put estimate term, and we can do like something like fill estimate greater than 0 and a geom call. Whoops, a plus geom call, like that. Nice. So let's do just like show legend equals false. Let's do fact reorder term estimate here. There we go. Okay, so this tells us, the things down here that are more from Hawaii, and then up here the things that are less from Hawaii. So these vowels starting with H, starting with P, starting with F and K, and then these things up here that are and GH, VER, ING. Like these are the kinds of subwords that are not associated with that they're not predictive of a post office being in Hawaii.
All right, we did it. We took this Tidy Tuesday data set on the United States post offices, and we took that input text data, which is the names, which is so short, like this very short text. And we created features for machine learning from the really brief text. We tokenized to subwords, and those subword features we used in our classification machine learning model to classify the post offices as to whether they were in Hawaii or not. This problem exhibited extreme class imbalance. So we had to account for that. And our results, were, I don't know, I think about maybe what I would expect, or pretty good, I think. But like these are the kinds of approaches we need to take when we have such problems with that kind of class imbalance. So I hope this was helpful, and I will see you next time.